Uh, Today we'll discuss torsion. Any member, mechanical member or any other member subjected to torque will have twist or torsion. Now this is a very important issue in engineering because there are many engineering components like shafts and other things which are subjected to torsion. Now components which are subjected to torsion develop shear stresses, and they are and they can fail if the stress developed within the material exceeds the limit or yield limit. So we look at the torsional problem. Now in the elementary strength of material, we have discussed this, but if you remember, we have discussed this only for circular cross sections. And there we have developed a simple equation that gives us the shear stress and the angle of twist. The equation is T by J equal to tau by R equal to G theta by L. This is a very well-known equation and we don't need to discuss much on this. But one thing you have to remember very clearly, that this equation applies only for the circular cross section, not for any other cross sections. And there are experiments carried out for other sections. The figure shows a rectangular cross section, and a torque is applied there. And you see that the torsion takes place in a different way than it does for a circular cross section. In a circular cross section, we assume that the plane section remains plane even after torsion. But if you look at this picture, which is an experimental picture with polystyrene foam specimen, that if you apply torque, there is a twist in the material, but the plane sections do not remain plane. There is a wrapping, warping in the sections. So obviously with this experiment and many other proofs, it has been understood that the method followed to develop the equation for torsion in plane for a circular cross section will not apply in this case. So here we have to understand that there is both rotation and warping. This warping was not there in the circular cross section. Now let's see how do we take care of this warping. I'll go through this once again just to emphasize that what is warping. Warping simply means that the plane sections do not remain plane. They also warp. And there is a twist. Twist is also there. Twist is there for circular cross section also. But there is no warping. Now to take care of this warping, we have to go through a different methodology. Now let's see what is that. Consider a circular cross section, just to give an example. And Sandvennen suggested that for deformation of any section of component with any cross section, circular or non-circular, we should consider both rotation and warping of the cross section. Consider the following member and take the origin of the coordinate at the top of the member x, y, z. And take any cross section and shown on the right hand side and take a point with the coordinate xy. So here x is equal to, and at a distance of radius r, x equal to r cos theta, y is equal to r sin theta. That is quite simple. Now differentiate this dx. So dx becomes minus r sin theta d theta. That means minus y d theta, that is equal to u, because displacement in the x direction, we normally assign u for that. So u, that is the displacement in the x direction, is minus y d theta. Similarly, we can differentiate y, and we can say dy is equal to r cos theta d theta, and that will be x theta, and that is equal to v. So the displacement v is equal to x d theta. Now, if we consider that the rotation of the component of the member given by theta is per unit distance along the z-axis. Here, there is a small mistake here. The vertical direction is the z, and this is y. So if we take it along the z-axis, displacement field will be given by u, that is the displacement in the x direction, is minus theta zy, because theta per unit is defined as the rotation per unit distance. So if you take the rotation at a distance z, so it will be minus theta zy, and v will be equal to theta zx. And now comes the w. W is the displacement in the z direction. Now this gives the warping, because if you go back to this figure, you can see that the parallel lines on the left hand side is becoming wavy, and that is warping, and that is given here mathematically by a function called warping function. So we denote the displacement in the z direction as theta psi xy. Psi xy is the warping function. So one, please look at it carefully. We are defining the displacement field in a component which is subjected to a torque, and hence there will be both twisting or rotation as well as warping. So for rotation, we define, or we can say that the displacement in the x direction is minus theta zy, and v, displacement in the is the displacement in the z direction is theta psi xy. Psi is the warping function, which is a function of x and y only, not z. Okay, so remember this equation one very carefully. This gives the displacement field in a component which is subjected to a torque, and we assume that here both rotation and warping is taking place. Okay, so having defined this displacement field, let us go ahead. Now here things are very simple, but I think it's very easy to lose control. So do concentrate and see what follow what I'm saying. So I'm repeating the displacement field here, and knowing the displacement field, we can define, or we can find out the strain. So epsilon x is the strain in the x direction, is given by del u by del x, and if you derive this u with respect to x, it becomes 0, because there is no x component here. Then we find out epsilon y, that is the strain in the y direction, and then again that is del v by del y. So if you derive v or theta zx with respect to y, that also becomes 0 because there is no y component here. And then epsilon z. Epsilon z is theta psi xy, and we are deriving this with respect to z. So del w by del z, that is also 0 because psi is a function of x and y only. So obviously, if you derive this with respect to z, it will become 0. So we have got 3 normal stress components to be 0. Now, let us find out the shear strains. Epsilon xy, as we know, is del u by del y plus del v by del x. Now, let us write del u by del y. Del u by del y is differentiating this with respect to y. So we get minus theta z. And then del v by del x, differentiating this with respect to x, we get theta z. So minus theta z plus theta z is equal to 0. So epsilon xy, which is a shear strain in the xy plane, is also 0. So you see, we have got 4 strain components 0. So only 2 other strain components, non-zero components, are epsilon yz and epsilon zx. So what is epsilon yz? Epsilon yz is del w by del y plus del v by del z. So del w by del y is simply theta. We are deriving this with respect to y. So we get theta del psi by del y. And then we have got del v by del z. So that means we are deriving this with respect to z. So we simply get theta x, and z goes out. So we take the theta out, and within bracket we have got del psi by del y plus del x, plus x. So this is the epsilon yz, that is the strain component in the yz plane. Let's go through it again. Del epsilon yz is del w by del y plus del v by del z. Now del w by del y is simply deriving this with respect to y. So if you derive this with respect to y, you get theta del psi by del y. So that's what we have written here, theta del psi by del y. Then we have got del v by del z, which is deriving this with respect to z. So deriving v with respect to z gives you theta x. So we have got theta x. So epsilon yz is theta outside the bracket and del psi by del y plus x. Remember, this x and y are the coordinates of the point where we are considering the torsion. Similarly, if we take epsilon zx is del w by del x plus del u by del z. So what is del w by del x? It is simply theta del psi by del x, theta del psi by del x. And then del u by del z, differentiating this with respect to z, will give you minus theta y, because z goes out, minus theta y. So take theta out, and we have got within bracket del psi by del y minus y. So we have got, out of 6 strain components, only 2 non-zero strain components. Epsilon yz is equal to theta del psi by del y plus x, and epsilon zx is theta del psi by del y minus y. I think it will be easy for you if you remember the form of this equation. because this equation we have to use quite often. Now, let's go to the stresses. Now, to find out the stresses, obviously we have to use the constitutive equation or the Hooke's law in generalized Hooke's law in 3D. So what is epsilon x? Epsilon x is 1 by E sigma x minus mu sigma y minus mu sigma z, and epsilon x is 0. So this expression is 0. Epsilon y is 1 by E sigma y minus mu sigma x minus mu sigma z is equal to 0. So that is also 0. Similarly, epsilon z is 1 by E sigma z minus mu sigma x minus mu sigma y is equal to 0. So because the three normal states components are 0, we can write this expression in terms of stresses. And when we look at the shear strain components, then we can simply write epsilon xy is equal to tau xy by g equal to 0, because we have found out that epsilon xy is also 0. And epsilon yz is equal to tau yz by g, and epsilon xz is tau xz by g. So these two are the only non-zero strains, and others are not. Others are 0. Now, if you solve this simple algebraic manipulation, you will find that sigma x, sigma y, sigma z, and tau xy. Tau xy is 0, that's very simple. You can see here, tau xy is 0. But if you solve these three equations, you will find out that sigma x, sigma y, and sigma z are 0. So we can say in a torsional problem, when a member is subjected to a torque or twist or torsion, then at a given point, the stresses will be of this form. Sigma x, sigma y, sigma z, and tau xy will be 0. So only non-zero stresses and strains are tau yz and tau xz, and non-zero strains are epsilon yz and epsilon xz. Okay, so remember this condition that we get from the previous consideration, that for a torsional problem, sigma x, sigma y, sigma z, and tau xy are 0. And we have got two non-zero stresses, that is tau xy is equal to epsilon g epsilon yz. Now, what was epsilon yz? If you remember this, if you go to equation 2, you will see it is theta del psi by del y by del plus x. So we have here tau yz is equal to g theta del psi by del y plus x. Similarly, tau xz is equal to g epsilon xz, and g epsilon xz is again theta del psi by del y minus y. So we write that g theta del psi by del x minus y. So simply by considering the previous two equations, 2 and 3, we can write the form of the equation of the two non-zero stresses, and given by equation 4 and 5. So let's remind ourselves that there are two non-zero stresses in a torsional problem. One is tau yz, that is given by g theta del psi by del y plus x, and tau xz, which is g theta del psi by del x minus y. Now remember, psi here is the warping function, and the condition for torsion is that sigma x, sigma y, sigma z, and tau xy are 0. Now this is from the Hooke's law or the constitutive equation. Now let us look at the equilibrium equation. Equilibrium equation. And the equilibrium equation is del tau xz by del x plus del tau yz by del y plus del sigma z by del z equal to 0. So this is the only equation of equilibrium which is not satisfied automatically. If you put this condition, for the equilibrium, 3 equilibrium equation, you will see that the first 2 are automatically satisfied. I think you can check it. It's not very difficult. And only the third equation is not automatically satisfied. So what we do is we substitute the value of tau xz and tau yz and see what we get in the third equilibrium equation. If you put that del tau xz by del x, that means you are deriving this with respect to x. And deriving this with respect to x, this is tau xz. Deriving this with respect to, deriving equation 5 with respect to x, you get g theta del square psi by del x minus del y by del x. Well, that will be 0 because y is not a function of x. Similarly, if we derive this with respect to y, that is del tau yz by del y, then you get g theta del square psi by del y square plus del x by del y, and that is also 0 because x is not a function of phi. These are only the coordinate points. Okay, so from the third equilibrium equation, we get the condition that del square psi by del x square plus del square psi by del y square is equal to 0, or Laplacian psi is equal to 0. So this is the condition that must be satisfied for any torsional problem to take care of the warping. So that's why we say that warping function must be satisfied, and this harmonic equation, for that this harmonic equation has to be satisfied. And it was shown here that the compatibility, constitutive, and equilibrium equation are all satisfied if we make sure that this Laplacian psi is equal to 0, or this equation, this harmonic equation is satisfied. So what this means is that for any torsional problem, we have to satisfy this harmonic equation. Okay? So far, let's go through this. What we said is, if we take a bar subjected to torsion, subjected to torque, then we have got the strain field given like this: u is equal to minus theta zy plus v is equal to theta zx, and w is equal to theta psi xy, where psi is the warping function. It is this warping that is the new term here, other than the things that we used for circular cross section. Now, with this, we find out the strains and stresses, and we find out that the force stresses are 0. sigma x, sigma y, sigma z, tau xy 0. That means for any torsional problem, these four stresses will not exist. Only two stresses that they will exist are tau yz and tau xz, given by equation 4 and 5. Now we have taken care of compatibility. We have taken care of constitutive equation, but we still have to take care of the equilibrium equation. Now, if we apply this in the equilibrium equation, we'll see that all the equations are satisfied except the third one. There are three equations of equilibrium for a situation where there is no body force and it's a static equilibrium. So only third equilibrium equation must be satisfied. In the third equation, del sigma z by del z will become 0 because del sigma z itself is 0. So the third term is not there. Only two terms that are there are del tau xz by del x plus del tau yz by del y. Now, if you substitute tau xz and yz from equation 4 and 5, you will find that we get an expression of del square psi by del x square plus del square psi by del y square is equal to 0. This simply means that the Laplacian of psi is equal to 0. That means to take care of the working of the shaft or the member, we need to satisfy this harmonic equation because other equations have already been satisfied. We have satisfied compatibility, constitutive, and equilibrium equation. Now, if we satisfy equation 6, then our torsional problem will be solved. Now, let's see how we do that. Now, here you have to concentrate a little bit more because some time ago we have considered stress function. Stress function are a group of functions or functions that automatically satisfy the equilibrium equation. Now, to solve equation 6, we need to find a form or the form of the psi. That means psi will be different for different problem, and hence we have to find out this function for different problem. But that is difficult. So what we do is we take care of, we use the stress function approach. Now, stress function approach is very simple. If you concentrate here, you will find out it's not difficult at all. We have the condition that epsilon x, epsilon y, epsilon z, epsilon xy is equal to 0, sigma x, sigma y, sigma z, tau x. Here there is some misprint. Sigma y, sigma z, tau xy is equal to 0. And the only two non-zero stresses are tau yz and tau zx. And the only equilibrium equation to be satisfied is del square tau yz by del y, but del square tau xz by del x is equal to 0. Now, previously we have said that from equation 7, if we use the warping function, we get a Laplacian equation, and if we satisfy that, then its problem is solved. But we go for a different route. We assume a stress function. We go for a different route because finding out the warping function is difficult. So we take help of the stress function. The stress function is easier. So let us find the stress function as follows. let's say that tau zx is equal to del phi by del y, and tau yz is equal to minus del phi by del x. These, it is defined in such a way that it will satisfy the equilibrium equation. You put this in equation 7 and you will see that it is satisfied. So that means these are the two stresses in terms of stress function, and the stress function is phi. So therefore, we can say that epsilon xz is 1 by g del phi by del y, and epsilon yz is equal to 1 by g del phi by del x. Isn't it? Well, we can put a negative sign here, or we can take the mod value. But the form is like this: 1 by g del phi by del y, and epsilon yz is 1 by g del phi by del x. So now we have written the problem in terms of stress function. Now why have we done that? This is because if we put it in the two compatibility equations that are not automatically satisfied, then we can find our condition. Now there are the two compatibility equations which are satisfied automatically except all compatibility equations are satisfied except this one, these two. Now, if we substitute tau xz and tau yz, and compatibility equations that are not automatically satisfied are equation 8 and equation 9. So we like to satisfy them in terms of the stress function. So look at equation 8. In equation 8, we have got del by del x, del epsilon xy by del z minus del epsilon yz by del x plus del epsilon zx by del y is equal to 2 del square epsilon x del y by del z. So here, if you see it carefully, the first term is epsilon xz, and we know epsilon xz is 0 in this case. So this term goes. And on the right hand side, we have got epsilon x, and that is also 0. So we are left with only two terms, and those two terms is del epsilon xz by del y minus del epsilon yz by del x, and we have got del by del x in front of it, and the whole thing is 0. So the same thing you will get if you look at equation 9. So what we get is that from the two compatibility equations which are not automatically satisfied, reduced to one equation, and this equation is del by del x, del epsilon zx by del y minus del epsilon yz by del x is equal to 0. Okay, so this means that the term within the bracket must be a constant. So del epsilon zx by del y minus del epsilon yz by del x must be a constant. So equation 10 is a term that we can use in our further calculation. So let's clarify it once again. Using the stress function approach, we can see that del epsilon zx by del y minus del epsilon yz by del x is a constant. So we use this, and we'll go back to now warping function. So don't get confused. We found out this constant using the stress function. Now we'll go back to warping function. Now if you remember, in the warping function was epsilon xz is equal to theta del psi by del x minus y, and epsilon yz is equal to theta del psi by del x plus x. So this was, just to flash back, this was there in equation 4 and 5. So we are going back to equation 4 and 5. So here, if we look at equation 10, equation 10 is del epsilon zx by del y minus del epsilon yz by del x is equal to constant. So our objective is to find out this constant. So substitute these two into equation 10. You will see that the whole thing comes down to a constant minus 2 theta. So now we know that the equation 10, the constant is minus 2 theta. Now, if we consider equation 7d and 10, 7d is only strains epsilon xz and epsilon yz, and 10 is equation derived from the compatibility equation. So combine equation 7d and equation 10, and we'll find out that it comes down to Laplacian phi equal to minus 2 theta. So let's understand this very clearly. When we used only warping function, we got an equation as Laplacian psi is equal to 0. So we need to solve this for solving any torsional problem. But what I said is, finding out a function to substitute for psi for a particular situation, for a particular problem, is difficult. But it is not so difficult for finding out a problem and finding out a function for phi. So phi means stress function. So we have found out another equation, which is Laplacian phi is equal to minus 2 theta. So let's be very clear. Instead of solving Laplacian psi is equal to 0, we are solving Laplacian phi equal to minus 2 theta. And that will solve our problem. Okay? I'll repeat this. We have already got an equation that is Laplacian psi is equal to 0, which needs to be satisfied for any torsional problem. But since it is difficult to find a psi function for a particular case, we convert to stress function. Because in stress functions are easy to find because there are many standard methods, and we find out that here we get a Laplacian phi equal to minus 2 theta. So if we solve this, then our torsional problem will be solved. Now let me give you some example. We said now there is a derivation for this, but that will be complex for you. But for the time being, just remember, for solving this Laplacian phi equal to 0, you need some boundary condition. Now the boundary condition here is that phi that is the stress function is 0 along the perimeter. If we take a circle or an ellipse or anything, then the stress function along the perimeter is 0. Why we need this? Because that will help us to find out the stress function. Suppose we take a circle. Equation of a circle is x square plus y square is equal to a square, say. So we can define the stress function phi equal to m x square plus y square minus a square. Simple. So this is the way we can find out the stress function for most of the geometries that we normally use in engineering. Okay, so we use the boundary condition phi equal to 0 along the perimeter to find out or approximate find out a stress function in terms of an unknown variable, which we'll find out later on. So here phi is equal to m x square plus y square minus a square. This m is a constant that we find out depending on the condition. Okay, so let's look at another important point. And here again, a little bit of mathematics is needed. I hope you will not get confused. Consider a cross section in the xy plane, and consider a small element at a coordinate of x and y. And as we said, that there are only two non-zero stresses, tau xz and tau yz. So we show the two stresses. So what is torque? Torque is force times distance. So what is the torque of this? Torque of this is tau yz, yz multiplied by x. X is the coordinate distance. X times tau yz, and that is anti-clockwise. And then we take tau xz multiplied by y, and that will be clockwise. So this is minus. And this is the total stress on this element. So we have to integrate this over the whole zone, and hence we write dx dy, which is the area, and we double integrate this. So when we double integrate this, this comes down to minus, we substitute the value of tau xz and tau yz. Here 1 by g del phi by del y and del 1 by g del phi by del x. So from 7d we substitute minus for tau yz minus x del phi by del x minus y for tau xz del phi by del y and dx dy. So we have got, we take the minus out and double integral x del phi by del x plus y del phi by del y dx dy. Now this is a double integral which can be written in the form like this, which can be written in this form. But we here what we are doing is we are writing it as two integrals, and if you look at it carefully, it's not so difficult. We are simply writing del by del x, x phi, plus del by del y, y phi. So we'll have two more components, and that will add up and will give you two double integral phi dx by dx dy. It's not difficult. If you sit down and do it, you'll get it. Okay, let's do it. If you differentiate this, what you get? You get x del phi by del x plus del x by del y, del x by del x, that is 1. So you get, if you differentiate this, you get del x, del phi by del x plus 1. And here, again the same way, you get del phi by del y plus 1. So you've got 2 outside, and we get 2 integral phi del x del y. So now we have got a double integral in split into 2 terms. Now this has to be reduced to a line integral, and there is a Green's function used, and in the Green's function, it's a simple way of reducing the double integral to a line integral. Is if you've got this, you get this integral is reduced to x phi dy minus y phi dx plus 2 double integral phi dx dy. This is not changed, but the first term is changed, it becomes a line integral. But then again, imagine or think of the boundary condition that we talked about earlier, where we said that the phi is 0 along the perimeter. So obviously in the line integral, this quantity will be 0 because phi is 0 along the perimeter. So the first term goes, and we are left with 2 into double integral phi dx dy. So this is the torque for any member with any given cross section. The torque will be given by 2 double integral phi dx dy. And we'll solve more problems later on, and you will see that things becomes very easy when you do it using the stress function. Okay, that's it for today, and we'll discuss more later on.